Did it start? Yeah. All right. So, homework assignment. How'd that go? Easy? Piece of cake?
Oh, yeah.
Once I figured out what I was supposed to be doing.
All right. Can somebody get the front light, please? All right. So, your assignment was to insert a node at a particular index, correct? So, if we're adding a brand new node, that's what the assignment was, right? Inserted index.
Yeah.
All right. So, let's say we're inserting a 9. Okay, so we have a brand new node. And we want to insert this guy at, let's say, position, let's say 2. All right, so we're going to try to add this new node to bucket 2. So what do we need to do? We need to traverse our list, 0, 1, 2. That's where we ultimately want him to be, correct? And then what do? This is all visual. Then we'll actually go through the algorithm doing this. So once we get to the right place, once we're here, we need to make this guy point to the same place that the current bucket 2 is pointing to. Then we need to make the current bucket 2 point to us. Actually, hold on. No, I'm doing it backwards.
Yeah.
Everybody relax. We need to make us point to the current bucket 2, right? And then make his previous guy point to us. Now we're the new bucket 2. Right? So 0, 1, 2. And now we point to the old bucket 2. That make sense? So that's what we're trying to accomplish. Now, let's talk about how we accomplish that. Okay, a couple different ways you could do this. First thing you can do is you can walk to bucket 2, and what I'm going to do is I'm going to create a pointer. I'm just going to call it Curr node. And we're going to have Curr node point to the same thing head points to. Okay? And right now we're going to have a counter. It's currently 0. Is 0 less than 2? Yep. Set Curr node equal to Curr node's next node. Increment our count. Is 1 less than 2? Yep. Set Curr node equal to Curr node's next node. 2 less than 2? Nope. We're done. We've successfully made Curr node point to the place we want him to point to. That is the node we're going to be replacing. Correct? Okay. Now, we have our new node here, 9, and we want this guy to do what? He's ultimately going to point here. So we're going to set our new node to point to the same place that Curr node points to. Like that. Okay? Now, what's the last step? The last step is we need to get this guy to point to us. We no longer have access to this guy. So what are we going to do? We're going to go back and do this math again. Except we're going to walk to this guy minus 1. So start back off at head. Is 0 less than 1? Yes. Curr node equals Curr node next node. Is 1 less than 1? No. So we're where we want to be. And what do we want to do? We want Curr node's next node to be equal to our new node. Make sense? That's one way we could have pulled this off. Alternatively, let's start by walking to -1. So we're going to go from 0 to whatever index we're going to -1. So is 0 less than 1? Yep. Is 1 less than 1? It's not. So we're where we need to be. Now, what do we want to do? Well, we want our new node, this guy, to ultimately point to this guy's next node. Does that make sense? So we're going to set our new node, next node, equal to Curr node dot get next node. Then we're going to set Curr node dot next node equal to me. See how that works? That's how we could do it with one loop.
Did we have a get next node?
We could have written it.
True.
All right, that makes sense? All right, so let's write both of these. We'll write the longer one with the 2 loops, and then we'll go back and write the single one. First of all, any question of what we're trying to accomplish? Okay, so let me back up here, because I think I definitely told you when I gave you the assignment to make sure you draw pictures, right? Yes? Okay, so we're going to write our code along with manipulating our picture. You'll find that's the easiest way to accomplish this. So we'll go into our code and linked list. No, 300. There's linked list. Okay, so here's our added index. So we already are dealing with what if we're adding to the front. No problem. We're already dealing with what if we're adding to the end. No problem. We already deal with what if we're trying to add to something that doesn't exist. Now we're at our else. Else we know we're going to be adding to some place that exists. So we're going to create a node called Curr node. Start this guy off at head. That's this pointing to the same place that head points to. Make sense? So I'll create a brand new variable of type node and made him equal to whatever head equals to. So we're both pointing to the front of the list. All right. Now, I need to walk this guy all the way to my correct position. I'm going to need a position for that, or a counter, some kind of counter. So I'm going to create an integer, int curpos. Start that off at 0. We'll say while curpos is less than index. Well, that's a true statement. What are we going to do? We're going to say Curr node is equal to Curr node dot get. We need a get next node to walk it.
Is there a reason why you didn't use a for loop there?
I could have used a for loop. So I need to go into my node. And in my node class, I need to give myself access to this private next node. So public node get next node. Okay. Now I can come in here and I could say Curr node is equal to Curr node dot get next node. And each time through, we'll say curpos plus plus. And he wanted to know, why didn't we just use a quick little for loop? We could have done that. We could have said for int I is equal to 0, I is less than index, I plus plus, Curr node is equal to Curr node dot get next node. So this code and this code ultimately accomplish the same thing. So I'll leave the for loop in, that's fine. All right, so after this line, Curr node points to the position where we are adding our new node. Did we already build the new node? We did not. Okay. So what are we going to do? We're going to create a new node. Node n is equal to new node payload. So we'll go ahead and build our brand new node. And what did that do? That gave us this guy. We built a node around the payload that was passed in. Okay? Now, what are we going to do with it? Right now, Curr node, if index was 2, currently points right there. That's Curr node. So we're going to set Curr node, well, we're going to set our new node's next node equal to Curr node. So what do we ultimately want to do? We want it to look like this. We're going to create our new node and set his next node equal to the same thing that Curr node is. So we're going to say n dot set next node to Curr node. Make sense? So we did that right there. Now, step 2 is we need to make this guy point to this guy. But in order to do that, we need to get to this guy. So we need to go back through and loop back up to -1. For int I is equal to 0, I is less than index -1, I++. But before we do that, we need to set Curr node equal to head. So reset Curr node. So what did we just do? We did this. We took Curr node. We don't need this guy anymore because we already made the correct connection here. So now we'll just reset this guy to point to head again. Then we're going to walk through our loop, ultimately getting us to here by going through index -1 to position index -1. So that's what this loop does. And we'll say Curr node is equal to Curr node dot get next node. So when we get here, Curr node points to the position immediately before where we are adding our new node. That's where Curr node points right there. So the current state of things is this. Curr node points to the guy right before index. We've already gone through the process of taking index and setting our new node's next node to him. Now we need Curr node's next node to no longer point here, but to now point to n. So we'll say Curr node dot set next node to our new node that we built up here. And then when this method ends, Curr node dies with it. And that's the new state of our list with our brand new node inserted at position 2. 0, 1, 2. The old 2 has become 3, so on and so forth. That make sense? So let's test this out. Take the lazy route there. All right, so we added a bunch of stuff. Let me just look at the current state of our list. List looks like 2, 5, 7, 13, 27. Let's go ahead. This is bucket 1, bucket 2. Well, let's go ahead and add something to bucket 0. So we'll say L dot add at index. We'll add a 1 at position 0. So now we should have a 1 at the beginning of our list after that. So we're testing our different conditions in added index. So this guy should get into this first condition. If index is 0, just go ahead and add to the front. Okay? So we'll run that. We should have a 1 at the beginning. There's our 1. Okay, our list currently has 1, 2, 3, 4, 5, 6 guys in it. So last position is position 5, right? If it's equal to index minus 1. Now, interestingly, I actually think we have it written kind of funny right now. If I say if index is equal to length minus 1, what are we doing? We're actually going to add it to become the new this guy. And this guy will actually become the new one later. Does that make sense? So if I say add a 12, add an index a 12, add index 5, we just set it to length minus 1, correct? For index. But it's actually going to add it to the second to last node, not to the very end. Oh, no, because we did call added end. We called add end in that case, so we're okay. Although it's not working logically, because in our previous one, if we add at bucket 0, this guy becomes a new bucket 0. If we add at bucket 5, he becomes the new bucket 5, but in this case, he's not the new bucket 5. He's the new bucket 6. Correct? I said add at bucket 5 out here in driver, but he actually will become the new bucket 6. So there's an inconsistency here. So that's 0, 1, 2, 3, 4, 5, 6. So we really need to say if they're passing in index is equal to length, add at the end. That make sense? That will make it the actual new end for adding at the end. Okay, good. So that became 5, but if I say add it to 6, it'll become the end. Okay. I think that's working correctly now. Not the end of the world. If you didn't make that change in your homework, it's not a big deal because it's what's confusing until you test it. Okay, so else we have our error. We tested that last time. Now let's start adding things in the middle. So let's go in here and we're going to add ll.add at index. Let's add a 9 at position 2. 0, 1, 2. There's our 9. And then there's the rest of the stuff. ll.add an index. Let's do an 11 at index 2. So we just replaced the 9 with an 11, pushing the 9 down to now bucket 3. Make sense? Okay, so this is one way we can make this guy work. Using 2 separate loops. Go through once, hook up part of it, go through again to the guy right before, hook up the rest of it. All right? Questions on that way? Okay, so that was an acceptable solution to the homework. Similarly, let's go in here and let's just get rid of all of this. So we're going to create a node, Curr node. Start this guy off at head. Go back to our pictures. Okay. Curr node points to the same thing head points to. Now, we want to walk up to this point, if, for example, if we're adding it to bucket 2. Okay, so we're going to walk to bucket 1. So we're going to say for int I is equal to 0, I is less than index minus 1, I plus plus. And each time through we'll say curr node is equal to curr node dot get next node. So that guy will traverse down the list by continuing setting himself to whatever his current next node is. All right, so that will put curr node pointing right here. Now, we need to build our new node, so we'll go ahead and do that. Node n is equal to new node payload. So there's our new node. That brought this guy into existence. Now what do? Now we're going to say curr node's next node. Well, we're going to say our new node set next node to curr node's next node. We want to make this connection. Okay? So we're going to say n dot set next node to curr node dot get next node. So that makes that connection. Then we want to set curr node's next node to n. Just like that. So that was probably the cleanest solution to the homework. So the entire assignment could have been done with the one exception of changing this to equal length instead of equal length minus 1. Could have been done in that amount of code. I suppose, plus adding set next node. Or, I suppose if you wanted to cheat, you could have just made this guy public. I'll make this guy public and pulled it off the same way. Then you wouldn't have needed a set next node because you could have just accessed the next node directly. Not recommended. You want a getter and you want a setter. What's the advantage of having getters and setters rather than making them public? Actually, let me ask you a different question. I called this a getter and I called this a setter. What are synonyms for those two words? What are the old school synonyms for setters and getters? Programming history. We talked about it when I introduced setters and getters. Those could be worth big points, big money. You could be in the running for today's big deal. What show is that? Is that Let's Make a Deal? What's the competing show? Price is Right. That's it. No answers? What are the synonyms for setters and getters? The old school version of those names. Setters and getters are so new age. It came with actually they didn't even come with Java. They came with like more recent Java. You know, the new programmers just started calling them setters and getters instead of the old cool names. A getter was called an accessor, and a setter was called a mutator. Accessors and mutators. Mutator being making it changeable, and accessor giving you access to it. Man, that could pop up on a test or something sometime. Hint, hint. What was it talking about? Oh, okay. So that's the solution to, well, a solution to the homework assignment. Anybody do it significantly different? I hope not. There's only so many ways. Well, you probably could construct a weird way of doing it, and that was just a complete waste of time. But I think this will pull it off.
I did it like kind of differently. I mean, essentially no, but I made like something that it returns a node at an index.
Okay.
It makes it head and then the index, and then it does all the loop in the node class and then in that method.
Okay, so you had the node. You create a method inside of node that let nodes traverse to where it needed to go and then hook everything up?
Yeah.
Okay. So instead of having a loop outside, you use kind of the pretend recursive calls to allow nodes to walk themselves. Mm-hmm. Okay. Okay. Any questions? How many of you got it working? 3.5 people? How many of you didn't get it working? There was pretty crappy voter turnout there. Well, actually, I started seeing the hands go up, sort of. Like so it looks like 3 people got it working, and like 9.25 people didn't get it working. How many people who? Well, let's see. Let's find out what kind of torture I caused. How many people spent at least 1 hour on it? Hopefully everybody. Who spent at least 2 hours? 3 hours. 4 hours. Ooh, loving this. 5 hours. Oh yeah, 6 hours. Oh my gosh. That's a full work day just about. Well, not for the Amish, but you know. Amish are putting in 23.5-hour days. And then they have breakfast.
They have breakfast, then they blink, and then they're back to work.
The Amish operate on the 60-hour work, the 60-hour day. Was that like from Men in Black? Was that the I think it was the 36-hour day. The two one-eyed guys that they had running the computer. You all saw Men in Black, right? You know, he said this is, you know, made up a weird name, and then Bob. Like, this is and Bob. I hate all of you. Okay. So, we've now added things to the beginning of the list, added things to the end of the list, adding things in the middle of the list. What's the next logical step? No, this is the easy way. I mean, what's the purpose of a linked list? Why does it exist?
So you can call it class and never have to do this.
No, I'm not going to let you do that for a while. See, you don't get to start using the class until you can complete this assignment in 3 minutes, as opposed to 6 hours. I'll let you start using the class once you can complete the assignment in 20 minutes.
Just this?
Yeah, just the add. But I mean, you know, you have to be able to do it naturally, not like it's fresh in your mind. You just copied my code. Although it'd be an interesting experiment to take somebody with the starting point for the assignment, and now that you have the solution, give you my code and see if you can finish it in 20 minutes without introducing random bugs. Because that always happens, right? That's what goes through your mind. It's like, well, my solution is identical to his, but it doesn't work, which means it's not identical. All right, so we now have the ability to add crap to our list. Might we want to remove crap from the list?
Focus.
Now, once it's in there, it's in there.
Once you enter, you can never leave.
All right, so let's write some remove crap methods. So we're going to write a method. Actually, before we remove stuff, let's write a method for getting something at a specific index. Because right now we don't necessarily have the ability to get a value out of the list. Not that we want to remove it from the list, but we might want to get the value at index 4. Just like working with a string or an array. Correct? So why don't we write a method, public node. We'll have it return a node. Public node get, and we'll give it an index that we're getting. All right, well, what are my options? If they say get index, if index is equal to 0, what will we do? Return head. Else if index is equal to what? Length minus 1. This one will be length minus 1. And we should say this dot length. Minus 1. Then what are we going to do? We're currently keeping track of tail, aren't we?
Why -1?
Because that would be the last legal bucket. Like think about when we're working with strings. Char at length minus 1 is the last legal character in a string. Our linked lists are 0 indexed as well. So if its length is 5, the buckets are 0 to 4. Okay? So we'll return tail. So ask for the first element, we'll give you the first element. Ask for the last element, we'll give you the last element. Else if index is less than 0 or index is greater than this dot length minus 1, now we have an error, right? So what will we do? We will throw a new Amish exception index out of bounds. The little tongue sticking out guy. Here we would give him the actual index that was out of bounds. Okay, and we're going to make a method throw an Amish exception. So if you try to access an index that doesn't exist, we'll throw an exception. Index out of bounds, we'll tell them what the index is and give them a little tongue sticking out face thingy. That's actually a naming convention that Java does not use. Got the whole class so confused you don't even get my geek jokes. All right, so these are the easy cases, right? Else, we're trying to access a node at a particular index. How would I do that? Let's say I was trying to access the node at bucket 3. This goes back to our programming patterns. We talked about these for, several semesters now, but definitely a lot last semester. Where many solutions look the same. Why? Because all hard programs are made up of a bunch of easy parts. And in this case, while we're solving a slightly different problem, one of the parts is identical to the solution to another problem. So we might use node, Curr node, starts off at head, for int I is equal to 0, I is less than index I plus plus, Curr node is equal to Curr node dot get next node, and then return Curr node. That make sense? Just like we did for adding at an index, I walk to the place that we're going to be replacing, but instead of replacing it, I just return that node. Is this the guy you wanted? Make sense? So that's what this else says. This else says you want a legal bucket that is not 0 or length minus 1. So, walk to the correct bucket and return it. Start off the beginning, walk to the right bucket, return that bucket. What's Curr node? Okay. No. Ish. No ish.
Oh, okay.
What's Curr node? What's the lineage of Curr node? Curr node is a variable. Variables hold values. What kind of value does this variable hold? A memory address. And that memory address points to what? The node in memory, right? It points to some node that was built in memory. Okay, and it happens to be the correct node that we want to return in this case. Okay, so understand the point of pointers, pun intended. I'm not at a good angle here. So let's say that we were returning bucket 1. This is index 0, this is index 1, correct? So through that for loop, I made Curr node point to the node, well, point to the memory address of the node that exists at bucket 1. How did I figure that out? By starting at the beginning of the list and traversing our list one time. That makes sense? What does it mean? Well, let me ask you this. What's the pointer count of that node? What is it, Tim? Want to take a guess at the question first?
42.
What's the pointer count of this node? Yeah, the node that's highlighted. This node. What's the pointer count of that guy? He's just stalling. You mean is the one that's highlighted? I mean, like something's in my eye today. What's the pointer count of that guy? And then tell me, what does that mean? Okay, no. I agree. Why? I could do this all day. Okay, the pointer count is 2. Why is it 2? No.
Because this is a 2 at the top left.
No. Unrelated. Do you definitely know?
Yes.
Okay, I'm not interested then. Do you definitely know?
Yeah.
All right, not interested. Want a hint? Rest of you? It dealt with the lesson on garbage collection, automatic garbage collection. So the pointer count on this guy, here, well, I'm just repurposing this box. It has nothing to do. All right, fine. I'm not going to fall into this trap. I'm going to create a brand new one. I'm going to put 2 in it, and we're going to drag them up here. So that guy's pointer count is 2. Why? What is pointer count used for? What is it? What does the pointer count mean? Say that again?
It's how many things are pointing.
How many things are pointing at this dude? That is exactly what the pointer count means. How many things are pointing at this guy? 2. Which 2 things? There's 2 guys pointing at this guy. Which 2? Okay, so Curr node points to him, and the node in front of him points to him. Does this node point to him? Nope. This guy points to this node. So what's the pointer count of this guy? Yes, the one that's highlighted, Tim. What's the pointer count of this guy right here? 1. Only 1 guy points to him. Okay, so the pointer count represents, it's just an integer that represents the number of things that point to this guy. Why do we need a pointer count?
Automatic garbage collection, it will pick it up if it's 0.
Yep, automatic garbage collector picks it up, cleans it up if it's 0. If nobody's pointing at this guy, that means it's dead memory. The memory address still holds a value, but since there's no way to get to that value, clean it up. It's unused. Does that make sense? All right, so this guy has a pointer count of 2 because 2 pointers point to it. At the end of this method, so when this method ends right now, what's the pointer count of this guy? What happens at the conclusion of this method? And all you need to look at is right here. Yes, Tim, the stuff that's highlighted. What happens at the conclusion of that method?
One of the pointers goes away
Why?
because the method, the thing dies in the method.
Okay, I agree. Why? I'm maybe belaboring it a little bit, but you're
Because Curr node was initialized within.
the scope of Curr node. The scope of Curr node is local to this method. So when this method dies, Curr node dies, which means at the end of that method, this link disappears, and this pointer count goes down to 1. That make sense? So that's the purpose of pointer count. So garbage collector will not pick this guy up. That would be very bad, actually, because we have not removed him from our list. We don't need the garbage collector coming by and just deleting swaths of our list. Okay, but it's actually an important point to make, because let's just say when we were adding stuff to our list, let's say when we added this 9, if we did things in the wrong order,
Strand him out
yep. Everybody relax. So if we do things in the wrong order, when we were adding this node, let's say we took this guy first. Now we have no way of getting to this guy. Does that make sense? As soon as we disconnected this guy's pointer count was a 1. Oh my gosh. my world. All right. As soon as we disconnected it, sound effects.
I'm not paying extra for that.
This guy became a 0. Now, does that mean he's immediately garbage collected? Not necessarily, just soonish. Because the garbage collection runs as a low priority process in the background. You know, it's not imperative that we reclaim this memory instantaneously. It's just imperative that we reclaim it eventually, because right now it's unused, it's unusable memory for all sorts of reasons. We can't create new memory there because the system, the operating system, thinks it's currently being used, and we also can't use what is there because we have no way of getting to it. Does that make sense? So it's just wasted space at this point. All right, but because of the order we did that, we made this guy unreachable. So we really needed to make sure that we hooked this guy up first. to this guy, and then make that connection. That way we maintained at least one pointer to all nodes at all times. Does that make sense? So that's where pointer count comes in. Out of curiosity, since a majority of the class didn't get this working, how many of you drew pictures? Keep your hands up if you also got it working. Most of the people who got it working also drew pictures.
So draw pictures.
I would be repeating myself. Didn't I? I said draw pictures at the end of class, right? In fact, I even specifically gave it as a hint.
That was also in the homework as well.
Was it? I said specifically in the text to draw pictures? Killing me. Very, very, very important. Especially when you're beginning at doing these things, you have enough to worry about dealing with the syntax and all this other stuff that it's going to be very difficult for you to conceptualize all this stuff in your head. So drawing pictures is going to be, it's almost like programming by paint by number. Okay? And it doesn't mean it's the easy way to do it. This is the only way to do it. I mean, when I sit here and write it, I'm drawing that picture inside my head. I've just done it so many times that I can see the linked list just from practice. You know, but when I first started doing this years and years ago, I drew pictures. Otherwise, you start getting lost. What points to what? Okay? So pictures are imperative for getting this stuff right. You spent 6 hours, and did you get it working? Killing me. You were spending 6 hours doing what?
Did it work?
No video games in there?
No video games, but in the background the Olympics were on, so they planned.
Oh, quad luge? You didn't watch quad luge?
Man, bobsled.
Bobsled. Yep. Yeah, except there was no big crashes. That upset me. Quad luge, you know somebody's going home in a body bag. Well, this weekend I watched, I think, episode 5 of Game of Thrones, where a dude decapitates a horse. New favorite show.
Oh, just wait, it gets better.
I know, I've heard. I don't even get the premise of the show, except they're decapitating animals. Now, first of all, I want to clarify that. If I knew a horse was actually injured, I'd be upset by it. But the fact that I'm confident no animals are harmed, I'm all about decapitating a horse fake. I'm all about fake decapitating a horse.
Fake.
Yeah.
I love fake decapitating.
Yeah, seriously. Man, how upset do you have to be about losing a joust to decapitate your horse? So awesome. Okay. So, anyways, we were talking about patterns. So inside of our get method, what did we do? We went through here and we find the node we want and return it. So if we come back out to our list here, what code would I write to display every single node in the list? Or to get every node in the list. Let's go that route. Here, I'll quickly write something here into, because I think we took our toString out. So I'm going to go ahead and write public string toString for each node. And what will a node do? It's going to return its payload. So each node knows how to return exactly its payload as a string. Okay. What's toString used for? Why did I call that method toString? Do you know the answer? Yep. Not interested. It's becoming a pattern, the people who know the answers. Tim? Take a guess at the question.
Typing, shut up. Yeah, still need the question.
Huh?
Yeah, still need the question.
You want to take a guess at the question? I have it highlighted. Why did I write why is this method called toString? Why did I specifically write a method called toString that returns a string? What's the purpose of this?
So you can take a node and make it into a string.
Okay, tell me more. Pretty sure you don't know what you're talking about, but possibly.
You take the value of whatever was in the node and then you make it into a string so you can display it. Easy.
Okay, but why did I specifically call it toString? It was very important that I named it exactly like this. Didn't we talk about this like almost an entire class, like 3 or 4 classes ago? I think so.
I think it was just 2 classes ago.
How are we supposed to write linked lists if we don't know the basics of the language after we spent an hour on this one topic? And the irony. Somebody who doesn't know the answer, tell me the answer. All right, what's the answer, Abe? See, now he's getting nervous. Like, do I know the answer?
Because it has to do with parents.
It does have to do with parents.
Because there's
And actually, the funny thing is there's so much evidence to the answer, like, on the screen right now. I'm going to make Abe sweat a little more. You want to take a shot here, Tim?
Is it because if you were just to say to display it, you wouldn't get anything, you just get memory addresses?
Why?
Because essentially you're just making, you're putting values into memory addresses, but it's not in the form of something that you can display.
Why?
It's just the way it is.
Did you say this?
Well, I told you a whole lot more than that. It shouldn't be difficult to answer. All right, go ahead.
So that toString method is an object, and you just overwrote it, where now it's going to return for a node instead of just returning that memory address, because that's what it would normally do.
Mm-hmm.
Now you're going to return the payload as a string.
Okay,
it's
so
going to call that when you use the print method.
So this guy is a method, correct? And by me writing this method, I overrode the method, this exact same method that I got from my parent, which was object.
Yes.
Okay? So my parent here is object. Why? How do I know that? Because I didn't specifically specify parent, so we know that we have extends object. That's the invisible ink up there. Okay? So we know this guy extends object, therefore he gets everything that an object has. And one of the things an object has is a method called toString. And what's the toString method do? It returns a string representation of this object. The default string representation is the fakey memory address thingy. We've now overridden that so that the more local version of toString returns the payload as a string. Okay? The punchline there is, why did I specifically choose this method? Because the print and println methods call upon this method for objects. Remember, there's a version of print and a version of println. So system.out.print, which is out is a print stream. So print stream has an instance method called print. It actually has a bunch of instance methods all called print. What's that called? When you have more than one method with the same name but a different number and or type of parameters, it's called polymorphism. So they have a bunch of print methods. They have a bunch of println methods. The print methods and the println methods cover all the primitive types and strings, and then they also have a catch-all for objects. They're able to have that catch-all for objects because every object will be guaranteed to have a toString method. Even if we didn't write it ourselves, we will inherit our parents' one that just shows the crazy memory address. Instead, we decided to write our own toString method here. And this toString method will return what we have envisioned a node displaying when it gets printed, when we pass a node to println. That make sense? So if I were to say node n is equal to ll.get, and let's get 2, whatever guy's at 2. And then I'd say system.out.println n, what will display? Ish. Will it be a memory address or will it be a payload? It'll be a payload. Why will it be a payload? What is n? N's a variable. It's a variable that holds a memory address. The memory address points somewhere up in memory to where an object is. What kind of object? Specifically, a node object. And the println method, this guy, calls this guy's, so there's some more invisible ink here. That's the method that's actually getting called in there. It calls that guy's toString method. And because we wrote a more local version of toString inside of node, it will call this guy's rather than the one it inherited from its parent. That make sense? If we need to access the memory address from our parent, what did we do? We said super.toString up here. That allowed us to build that list that contained the memory address followed by a colon followed by our actual payload for a node displaying itself. So when we wrote the display method, we wrote it such that a node would display itself and then display its child. But we just want a node to be able to display just itself. So that's where this toString thing comes in that we just wrote. So out here in driver, we're going to access whatever node's at bucket 2, then we're going to display it. So it should just display the payload. 11. That make sense? If we wanted to have the memory address in there as well, we can say super.toString concatenated with, let's just do a colon, concatenated with the payload, and now it'll display memory address-y payload. Does that make sense? We went ahead and accessed the string version of our parent. That boils down to a string that looks like a memory address, and then we built a new string out of that. That included that memory address, a colon, and our payload. Make sense? Okay, so does anybody not understand that? I'm about to give you a quiz, so you should ask your questions now.
What's the meaning of life?
42.
All right, so that's how you get the length of a linked list. We wrote a method called length, and it will print out 7. There's 7 elements in there. Everybody take out a piece of paper. Write the necessary code to display each element of our linked list to the screen without using the linked list's display method.
with what we just wrote with that toString.
Basically, everything you need to complete this assignment is in these 3 lines. Okay? You cannot use the linked list built-in display method that we wrote that puts all the little arrows in there. I want you to display every element of our linked list, 1 node per line, just to the screen. Everything you need to solve this is what's already in your head from basic programming and these 3 lines. You have 5 minutes. Oh. So 1 more minute. All right, let's have them. Make sure your name's on it. Is it easy?
No.
Why is this row completely omitted?
Nobody likes that, bro.
This is bad luck.
Because I sat there once and I don't sit there anymore.
All the people that were supposed to be there got scared and ran away.
I got wrist switch out room.
So that should do it. There.
I like adding one extra line.
All right, questions about that?
Can we take the quiz?
Easier than you expected it to be? So now, for your homework assignment.
Write that method again.
No, you wish. Add to your code. Remove front, remove end, and remove an index. I will give you my code as a starting point. Okay, so you'll have the same code we've been working on in class. I'll even leave, I'll just zip up the whole folder. And so I'll even leave this example out here in driver. But you'll have everything up to right now that works for adding at a node and getting from a certain node. Getting from a certain position. Make sense? So you're going to be adding at least 3 methods. Remove front, remove end, and remove at index for Thursday.